Now, you see and you can see the signature of what we are seeing here in the time series, time trajectory series. This beautiful thing that happens. Okay. So now we know that hydrophobic collapse alone can form an ordered state. So let me go a little bit deeper into that. Is there an nucleation of collapse state? How does it happen? So there's a movie here which is not there anymore, which just shows really very large extended chain, C100 polymer chain, but now it's a Brownian tunnel simulation. It forms a nucleus of collapse in the beginning that moves around the chain because the homopolymer. And then it forms one here, then that goes away, but this one becomes bigger. Then one forms here again back, but little bit inside. And this, once it grows certain critical size, that becomes stable. Okay. And then these things like a soliton can move along the chain. And they kind of collapse. And then once they form a stable core, they pull everything in. And then you find the same collapse structure. So there are indications of nucleation mediated folding that people talk about a lot. Now I go a little deeper into hydrophobic effect. How does this hydrophobic collapse take place? When the two hydrophobic groups come together, do the water move away? How does it happen? There is a theory, very effective theory, a very nice theory by Bloom, Chandler and Wicks. They said there is a drying transition. If you have two plates, you bring them together, then beyond a point, water just evaporates and you get it collapsed. It's a very, very interesting phenomenon. Drying transition that happens when you bring hydrophobic like paraffin wax together. And water in between just disappears. This is called a drying transition. Is there any evidence? People are a lot of controversy on that. And then in 1982, there is a then England, now in Australia, Israel, not Australia, I think somebody told me he's in Sandy around. In between, I think he was in Australia, but an experiment was done in Cavendish laboratory, Israel. He really did a beautiful experiment by putting two plates and then measured the force. That was the beginning, I think, of the first stage of this kind of microscopic calculation, but that was a different and very difficult. It was done by AFM later, this force. And he found indeed there is a long range, little understood force, attractive force between the two hydrophobic plates when there is water all around, even inside. So this came to be known as hydrophobic force law. It varies exponentially with distance. That means what happens is that if the d is the distance and water everywhere, if this is the distance, then if I do the d, then this is attractive and the force goes to 0. And in this direction I say negative, so it's negative. It goes like that. And this can be fitted in a quasi-exponential, it's a little bit richer than that. So now I want to study these things. So this first study was done which was published this year, and now we're doing last year, and we've done something more with this person Shamantu and the result I'm going to show you is not earlier, but more recent, not published yet. So hydrophobic force law has become a very big thing. People are measuring with the FM, with the gold tip here, bringing to a surfactant and finding the force between them. Many measurements happening like that, putting salt concentration other than. All of them find indeed there is an attractive force, which is not van der Waals. This is van der Waals, which is fairly short range, but they find much longer range hydrophobic, experimental hydrophobic attraction, and something like this decay, some find bigger decay. So this is the kind of, as I said, quasi-exponential attractive interactions, both in between between the and quite large force that they find between the two plates. How to understand that is effective attractive force? So understanding of hydrophobic force is the negative question: is there evidence of drying transition? That theory says, and a lot of simulations are do. The study of hydrophobic force law, many people have studied it, and so I'm going to do it now a little bit more systematically. It turned out nobody studied in simulations this distance dependence between the two plates. So I have water everywhere. In between the two plates, I have water here. and I am going to put this into two plates. They are layered on spheres. The plates are smaller size, like 1.4 angstrom, and here, and this is, and I bring them together. Difficult simulation, painstaking and takes very long. So and we then do, we use virial theorem, virial expression to get the pressure on this from everything, pressure from that everything. Then we projected the pressure in this direction, and then we see the what is the force related to that. It's easily said, but very difficult to do. And this is the result now. The hydrophobic force and attractive with this kind of shape. What is interesting here, that this region and this region is slow, and there is a crossover between them. This is the one Israeli detected, which is about 2 nanometer. He said little longer, 4-5 nanometer, 2 nanometer. This is the one with Lumul standards say, and this is less than a nanometer, like 5 angstrom. And I'll show you some real video. The crossover is having the signature of drying transition. I brought the 2 order parameters. One is density here in between the plates, the average density. And as I change the D, this is large, this will be probably 10, 15, 20, 30, something like that. By the time I go to 30, I find these oscillations, this is very close to each other. There are no water very close to the plate, no water because the hydrophobic close to the plate. Then there is a layering peak. In between there is nothing, there is a destructive interference between the two, and that's a very important thing. They orientationally they oppose each other, and then many oscillations come, and then you find out, and as you go on increasing, one is the bulk density, you approach the bulk density asymptotically. And then this is another order parameter, which is the orientation order parameter called tetrahedrality. I talked about it yesterday, how tetrahedral the arrangement of individual water molecules. It's nearest neighbor. This orientation order parameter is a very important role it plays in freezing, melting, and all properties of water. Here also we see in bulk water it is 0.63. Somewhere here is the bulk, and this is about is 20 or so, and your orientation arrangement, orientation order, magnitude of orientation order is depressed, and this is the reason of your hydrophobic force law, because that is enthalpically. So this is again now the total density I'm plotting against, and they have the same kind of behavior, quasi-exponential. Now comes a really very interesting graph. We now calculated, we made another difficult calculation, we made a coarse grain, and then in a coarse grain, in the region within the plates, I made it into little cubic boxes, and then I calculated the density fluctuations. And then I got the local compressibility. And then I plotted the local compressibility against the distance between the two plates, D, which is dBm. Look at that, what happens. Here, this goes over to bulk value. And then, when it comes around this 15 angstrom, there is a huge growth in the compressibility, like a phase transition. And then the gain comes down. This part below 5 is not realistic because they are almost touching each other. But this is still has some physical meaning when they are 10 apart. We have a couple of water layers. So here it is vapor-like, here it is liquid-like, and there is a liquid-vapor kind of a transition going on. We still don't fully understand it, but it's a little away from coating folding, but it's a very, very nice result. Okay, back to coating folding. So potential. So what we want to know now, which is in the hydrophobic force law also, what is the effective interaction? What is the effective attractive interaction between two hydrophobic forces? One of the things that we did when doing something else, kind of things, different area but things kind of together, is that if I take 2 methane molecules in water, then what is the attraction between them? And then that is an interesting structure. So the effective attraction is called potential of force. How they attract each other. Effective, because you have removed the effect of water. The effect of water is there, but when you are talking of 2 methane, you talk only the distance between them because there's VS. So they act as the minimum here. So this is the hydrophobic effect, that they attract each other much more than what you take from their own intermolecular interaction. And however, when you did these kind of things and try to understand protein folding, it doesn't work. Most simulations of protein folding go on doing hundreds and hundreds of simulations. Like when HP36 is small protein, we simulated 680 or 86, 686 trajectories, we got 3 or 4 net price state. It doesn't work. And we are wondering why it doesn't work. At that time, I was doing a water liquid crystals. And the liquid crystals, we had the orientation dependent on potential, and there is a model called Biman potential. It's very, you should know these things. The Lennard-Jones potential is a standard thing, but you can extend that to take ellipsoids. Two ellipsoids now depend whether they are parallel, they are like T-shape, okay, they are anti-parallel, depending on there is a polarity in the model. It's a very nice model. How to talk of interaction, not in a Lennard-Jones spheres, but in a, when there is a orientation dependent. So that was the time Professor Shariga was visiting Bangalore, and we just about got some work done. So I went to see Professor Shariga. He was really impressed. He said, we are just doing this, you know. Actually, we are just doing this thing. And he was impressed, but even then, even he has not fully put this thing into, and we are now again gone back to this problem. We have gone back to the student who did it, Ono Mukherjee. And one of my students now in Pune, we are trying to do it, but let me tell you what we are trying to do. Some published, some yet to be published. So now we are doing a really realistic potential, much more realistic than any of those implicit model or so-called Go model or the structure, much better than them, but much more difficult. So here is the polypeptide chain, and amino acids now, I replace them with ellipsoids, folate, oblique. So this is the full beast, except I want to replace the interaction between them by an effective interaction. I also need to take interaction between these things in that now. Okay. I expect certain kind of excluded volume interaction between them, or from here we could do. But real packing, I know in protein folding and between these amino acid sites, they are packing like in alpha helix and beta sheet. How do I do them? One of the way that we try is the following, that we, and there is a technique, I'll give the reference later, developed by some other people. They broke the, say an arginine, they broke it into essential groups. Like CH2 is essential group, CH is an essential group. So you like a united force field model, you take out CH, you group them a little bit more coarsely, and then you go to protein data bank, just like Lennard-Jones did a couple of 100 years ago, formulate, or 150 years ago, formulate intermolecular potential. You go to protein data bank and try to form the probability distribution between them, invert it and get this called get the potential. This is called knowledge-based potential. And lo and behold, okay, I sorry I don't tap any other, nuked everything. There's a beautiful result that comes out. I really like this, which is my favorite, lysine, which is the positively charged, right? You get the completely, well, quite negatively as well, it doesn't matter to me at this point. Full of potential come out. It's hydrophilic guys are supposed to repel each other because each hydrophilic guy likes water. So another hydrophilic guy likes water. They don't need to come close to each other. They are very happy with solving. So we say hydrophilic groups repel each other, and you see the beautiful pool of potential that comes out. Different orientation of the lysine. And here comes our friend phenylalanine. Strongly attractive, very strongly attractive. In KBD week 16 at that, when they are parallel to phenylalanine, this I should see plays a very important role. And when you got T-shape, you have this kind of potential. Then you go different orientation. Essentially, when you have alanine, like phenyl groups are pointing to the opposite directions, they are just opposite. But this is all coming just from protein data bank and this knowledge-based potential. Okay. One is arginine, and we are really surprised that the arginine has an attractive thing. There we realize that because arginine can form hydrogen bond, because there is a positive charge distributed on NH, this tail of the arginine, and then that can form water. There is a water in between. But there is one more thing. Arginine has a tail, hydrophobic tail. That can also play a role. Okay. So one go into different things like histidine, tryptophan, and those metalloproteins. Histidine is in metalloproteins, and there's a beautiful things that come in tryptophan and histidine. Really beautiful stuff that happens. So again, I'm not going to talk about that. Now, so I now go this phenylalanine, and orientational potential of beam force of phenylalanine will be essentially major part of the remaining talk. So this phenylalanine here, that when they parallel to each other, they play a very, very important role. Okay.